Okay, thank you everyone for joining us today. Today we're going to talk about passive design and running environmental climate assessment on your projects. So the purpose of this training is actually for the design competition, which we're really excited about, that this design competition is actually going to have a sustainability component and that every team is going to have to run a basic climate assessment for Santiago de Chile and interpret the information and apply that to their design. So we're really excited about that, but I just also want to say that this same assessment can be applied to and should be applied to every project across Perkins Eastman. So what we're laying out here today in the training is broadly applicable for everyone. Our agenda for today, we're going to start with a basic intro to passive design. Then Juan's going to jump into actually running the climate analysis and show you how to run those scripts. Then we'll both be looking at how to interpret the results once you get the information generated, and then how to apply it to design. So jumping into passive design, the very first thing that we need to consider when starting a project is the basic climate zone. Where's our project located and what's the basic climate data associated with that region? So as you know, there's a variety of climate zones across the US and internationally as well. And each of these climate zones, whether it's hot and dry, hot and humid, cold, will have very different passive design responses to deal with the outside climate conditions and to create a comfortable interior as a result of that. Now, there are some basic rules of thumb that can apply across climate zones. So in most locations, elongating your building along an east-west axis instead of along the north-south axis provides a lot of benefit. It allows you to more easily shade your building or accept heat into your building to reduce heat gains and to improve daylighting throughout the space. So in general, this is probably a rule of thumb that you were taught in school. That's a very good strategy to follow. But this can be slightly adapted depending upon the climate zone. So as you see on the right, in a very cool climate, you might want to shrink the floor plate as much as possible to create a really compact building with very little exterior surface area. Whereas if you're in a more tropical climate, you would want to elongate the building even more, allow for more openings and cross breezes to occur to really bring air into the building and through it. So let's look at some of those different responses by climate zone. One of the best ways to get an idea of what a smart passive design strategy should be in your particular climate is to look back into vernacular design. So for instance, in a very hot and dry climate, a lot of times there was very thermally massive surfaces that were used. That would be well shaded during the day to keep the interiors cool as temperatures rose, but then able to kind of re-radiate that heat into the interiors at night when temperatures dropped. So in very dry climates, temperatures are very hot during the day and they fall at night because there's very little humidity in the air. So obviously shading is an important strategy, thermal mass may be an important strategy, and also allowing air to flow through, up and out of your building is very important. So using kind of open screening devices that can allow this air to come in without the light might be a helpful strategy here. Now in a hot, wet climate, similar to when it's hot and wet outside, you might put on some rain boots and carry an umbrella. The vernacular buildings in these regions also look very similar. They're often elevated from the ground, and they have large kind of canopies that are protecting them from the rain. But another big part of them is really making sure that there's still airflow. So there's air that can come in from underneath the building, move through it, and exhaust through the top. So that's to deal with the heat, but still protect it from the wetness of the climate. Now in a cold climate, similar to how you'll bundle up so that there's really very little skin exposed to the outside conditions, the vernacular buildings in these regions are very similar. They'll have very little openings to the exterior, very few windows or doors, because that's where you're going to lose the most of your heat. And they might be more bulked up or insulated, potentially even using, like in this circumstance, earth sheltering techniques to further insulate themselves from the exterior. Now, in vernacular architecture, when there was no HVAC or lighting, the buildings were designed to deal with the climate conditions because they had to be to create comfortable interiors. When HVAC and lighting were created and became more proficient throughout the country and throughout the world, then we were no longer reliant on exterior climate conditions to deliver comfort. We could entirely enclose our buildings and um, uh, close them off from the exterior with very few windows because we were able to provide electric lighting within these spaces, and we were able to provide air conditioning or heating when needed within these spaces. So that was a response. This is actually a school that we have since replaced, but it was a response of the age where we no longer needed the sun, we no longer needed air. We could deliver that ourselves, so we kind of closed off our buildings to the perimeter. Nowadays, we know better. We know that daylight and views are important to providing wellness, and connection to the outdoors is actually necessary. But we've kind of gone to the other extreme where we're totally encasing our building envelope in glass. And in actual fact, we're relying even more now on HVAC systems than we might have been in the past. Simply because glass is not a very good insulator, and we're having to deal with creating comfort at a much higher level because of the poor insulation that glass offers. So obviously this is an extreme, and what we would be looking for in applying passive design strategies in this day and age is to not take it to that extreme. So this is just a little life lesson from a cat here. When a cat's cold, what do? They go into the sun and warm themselves up. When we're cold, what might we do? Well, we go to the end of the earth to dig up coal or pull oil out of the ground and send it to a refinery or into a power plant that's miles away, and then through power lines it comes to our house, and then we kind of get in bed under our electric blanket, plug into the wall, and connect to that energy to deliver heat. There might be a much more simple solution. We could just go outside, or we could use the free resources that are available from the sun to help heat us and to help reduce the amount of energy that we're using in the process. So, applying this to architecture, the upfront decisions that we make regarding the shape of the building, regarding its orientation, its massing, its fenestration, is it all glass or not? These actually have a big impact on the ultimate energy performance of a building and ultimately the comfort that will be delivered in that space. So if we make these smart decisions up front, if we respond to our climate appropriately and we apply passive design strategies, then later on we can use smaller systems that cost less money, and add smart systems, and we're more likely to reach higher levels of performance at that point. So sustainability and passive design in particular is not just about adding mechanical strategies and putting PVs on your roof to create an ultimate impact. You really want to start with the basics. So with that, we'll jump over to actually running a climate assessment. And for the purpose of this study, while Juan is pulling everything up, we're not going to be using the climate of Santiago de Chile because we didn't want to give anything away. So we're going to be running an assessment with the Boston climate in mind instead.
Perfect. So as Heather was saying, one of the most important things in order to do a passively designed building and a sustainable building is understanding your local weather and understanding your local climate conditions. So it is really important since the early stages of the project for the teams to understand where the wind is coming from, how the sun is impacting your site, and how the different climate aspects of the region are affecting your building. So we're going to run, as Heather was saying, a very brief example of how to run a climate assessment with grasshopper, with ladybug and honeybee more specifically. So this is a Rhino interface for those of you who are not familiar. First thing, the most important thing, as soon as you open a Rhino window or Rhino, the first thing you got to do is here, up here in the command line, you got to type units. and this window is going to pop up. Unfortunately, the only way in which Grasshopper, Ladybug, and Honeybee are going to run is by setting your units into meters. So this is an extremely important component. You click meters and you click OK. How do you know that your project and your interface is under the unit meters? You go down here to the bottom left corner and you're going to see that meters is going to show up in this little rectangle. So once you've set up your units, you're going to go into Grasshopper, again, command line, and you're going to type Grasshopper. You click enter, and this window is going to show up. This is the regular interface of Grasshopper for those of you who don't know how to use, who've never used Grasshopper before. So first thing we're going to do is that we're going to click here, open document. We're going to go into our S drive. We're going to go into the folder that says create. We're going to go to the scripts library. We're going to go to the Grasshopper library. And we're going to go to the en_climate data. So before I open the file, I want to point out that this script has been a progress and a development from the data unit. We've been working hand in hand with this newly created group called the data unit, and we're developing scripts not only from a sustainability and from an environmental standpoint, but we're creating scripts in order to simplify your programming, to generate shapes, to make your building more efficient, to get data out of your projects and out of your models. So all those folders and all this drive, all this scripts library are going to have all the scripts in the upcoming weeks. So stay tuned and we'll keep you posted on how that goes. So as soon as we get here, we're going to double click here where it says weather data script, and we're going to open it. It's probably going to take a couple of seconds to open. And on the meanwhile, as Heather was saying, we're going to use the Boston weather as an example for this particular exercise. So what we're going to do is that I'm going to show you how to get your weather file. There's a folder in that same location where we open our script with all the weather files. But in case you're interested in getting a different weather file, you're going to type Ladybug EPW map in your browser, and the first web page that shows up is going to be a map of the world with all the weather files and the planet in existence. So for this particular exercise, what we did is that we go here, we go to Massachusetts, we zoom in into Boston, and we click in any of these dots over here. I'm going to click here, for example, and I'm going to say download from DOE. Click here, and it's going to download a zip file. If you click into that zip file, you're going to see there's different files. The file we're interested in is the EPW file. This is the file we're going to link into our script. But for practicity, as I was saying, all of these files are already preloaded into the S folder, create, scripts library, Grasshopper, climate data. And right next to where the script to the weather data script is, you're going to see a folder with all the weather files from almost every part of the world. So as I was saying, we're interested in the United States and Massachusetts, and we're going to preload this one, the Boston EPW file. So going back to Grasshopper, this is what the script looks like. I'm not going to go into the depth of what each one of these components mean. I'm just going to show you real quick how the script was set up and how to link your weather file into the script. So the first part is going here to the left part of the script where it says local file and computer. You're going to click here in this component, right click, select one existing file, and we're going to go again into the folder. And in the folder that it says EPW weather files, we're going to click United States, Massachusetts, Boston, and we're going to link the EPW file. So as soon as you click that, you click open, and it's going to take a second. It's going to take a couple of seconds to load the script, to load the weather file. Wait for it. And there you go. We minimize this. You should be able to see all the local weather information in your screen. So those are a series of charts, and I'm going to go into detail later on what each chart means and how to interpret. That tells you how your local weather is performing and the local weather data of the city you're interested in. So going from bottom to top, you're going to get the windroses, the yearly windrose, and your seasonal windroses broken into winter, spring, summer, and fall. And you're going to get the legend that's going to show you what each one of those colors represent in terms of airspeed. Then you're going to have your Universal Thermal Comfort Index chart or your UTCI chart. This chart is going to tell you pretty much thermal comfort levels throughout the year, and it's going to tell you if you're going to experience cold stress, heat stress, or thermal comfort. Moving on, you're going to get the temperature chart that's going to show you, again, based on the colors you're getting on this legend, if the year is cold, if the year is hot, and what parts of the year are, and the temperature you're getting throughout the year. Moving on, you're going to get the relative humidity chart, same thing. You're going to get, depending on the color, different levels of humidity from 0 to 100%. And finally, you're going to get the psychometric chart. And we're just going to explain in a minute how to interpret this chart over here. But this is going to plot pretty much all your passive design strategies in the psychometric chart. So moving really quick, all of these charts are located here. All of these components are going to show you those charts. This one over here is the seasonal windroses. This one over here is the annual windrose. This one over here is the UTCI, or the Universal Thermal Comfort Index, temperature, relative humidity, and psychometric chart. Again, you don't have to modify anything here. This is preloaded. In case you're interested in like playing around or you have some grasshopper experience, there are some parameters you can change, such as the time range in which your analysis is running. By default, it's going to run a yearly analysis, but if you want to test different periods throughout the year, you can modify these sliders over here. And this chart, this component over here is also a very important component. This component is going to plot the different passive design strategies in the psychometric chart. So again, each one of these tick marks or check marks is a polygon within the psychometric chart. So you can turn them on or turn them off. You just click into the check mark. It's going to take a couple of seconds and it's going to disappear from the psychometric chart. Or you can click on it again and it's going to plot again into the psychometric chart. So I'm going to go into the details and what each one of these graphs represent. So the first graph, temperature graph, I'm going to explain you how to read this graph. First thing and most important, it goes from bottom to top. It goes from AM early in the morning till PM at midnight. And it goes from left to right. It starts in January the 1st and it finishes in December the 31st. Really important, your legend. Your legend is going to show you and tell you what each one of those colors in the chart represent. And it's going to go from 6 degrees Fahrenheit to 100 degrees Fahrenheit. Blue colors represent low temperatures, red colors represent high temperatures, and the white spots you're going to see in the chart are what ASHRAE defines as comfortable temperatures that range from 68 degrees Fahrenheit to 75 degrees Fahrenheit. Almost a similar approach with the relative humidity chart. Again, it goes from AM to PM, from early in the morning till midnight. It goes from January the 1st on your left side of the chart to December 31st on the right part of your chart. Really important, your legend is going to show you what each one of those colors represent. It goes from 0% to 100%. The blue colors represent low relative humidity levels. The red colors represent high relative humidity levels. And again, the white spots represent the comfortable humidity levels based on ASHRAE standards.
So real quick, sorry, before we move on, what does this mean? So for Boston, if you go back to the one before, for Boston, this is showing us that there's a large chunk of the year that is under the comfort zone. So that it's in the yellows, it's in the blues, meaning it's lower temperatures than the comfort zone, and there will be a need for heating to provide that comfort. So essentially, this is telling us that, if we want the most bang from our buck in Boston, we should focus on passive heating strategies. If you go to the humidity slide, this is also telling us that Boston has a fairly humid climate. So it's not a very dry heat, and it's not a very during the summer. And so there are some passive cooling strategies which wouldn't be recommended here because of the high humidity levels.
Correct. And the compilation, or pretty much the holistic way in which we can take a look at the temperature, humidity, and all the climatic factors and environmental factors that affect thermal comfort can be seen in this chart. So pretty much this is the UTCI chart, the thermal comfort index chart. Again, you read it from morning till night, from bottom to top. You read it from left to right, starting January the 1st, finishing December 31st. Your legend is a little bit more simple. It's just going to tell you which parts of the year are generating cold stress, which parts of the year are generating heat stress, and which parts of the year under thermal comfort. And the blue colors represent parts of the year that are under cold stress, that are going to generate cold stress. The red parts are going to generate heat stress, and the white parts are going to be under thermal comfort. So based on ASHRAE standards, thermal comfort is defined by 6 factors, and most of them are included in this chart. So relative humidity is included here, temperature is included here, solar radiation, solar exposure, wind speeds are included here. So this is pretty much a compilation in a more holistic way of understanding your local climate. And as Heather was saying, you can see and you can interpret from this chart that Boston is predominantly a cold city, and that 6, almost 7 months throughout the year, you're going to be under cold stress. So this is going to tell you, and it's going to give you a clear picture of how to design your project. You're going to have to focus more on passive heating design strategies rather than cooling design strategies. And to be fair, the heat strength throughout the year is so minimum that you can almost get away without having an air conditioning system, a cooling system that's going to provide mechanical cooling to your building by just designing an efficient building that accounts for natural ventilation, that accounts for cross ventilation, that minimizes heat gains, that has a proper window to wall ratio. And again, part of what we do is understanding our local climate and the local weather, but it is really important for us to account for climate change and to understand how our site is going to be impacted by global warming in the next 30, 50, and 60 years. So in the same folder where you're going to get the Santiago weather file, you're going to be able to see the weather file for the year 2050 and the weather file for the year 2080. And I'm actually going to show that right now. So if you go, again, to Standards, Create, Scripts Library, Grasshopper, Climate Data, and you go into the Weather Files folder, if you go to South America, there's a folder called Santiago. That folder has 3 subfolders. One for the weather file from nowadays, which is this one, but it also has the weather file for the year 2050, and it also has a weather file for the year 2080. That way you can run the same weather analysis we're seeing on the screen, but for the years 2050 and 2080. So what this is telling us pretty much is that there's a lot of comfort hours, especially in the fall, in the summer, and in the early spring in Boston. However, this tends to get reduced by the year 2050, and it's almost going to be non-existent by the year 2080. So all those white spots that represent thermal comfort and thermal temperatures, comfortable temperatures, are going to be eliminated from 6 a.m. till 6 p.m., which is the bulk of the day. And the winters that tend to be like colder in January and in December are going to be warmer. So all this blue, dark blue colors you see in January and December are almost going to disappear in January and December by the year 2080.
So it's important to note a few things about this. One, when we're designing our buildings, we want them to be 50 to 100-year plus buildings. So taking the future impacts of climate change in mind when we're designing our passive strategies is really important. We want to make sure that our buildings are able to survive when temperatures do change. The other thing to note here is climate change is going to impact every city, every region differently. So whereas in Boston, temperatures are rising across the board, so it's making the winters warmer and it's making the summers warmer, there are climates across the world where that's very different. So like in Quito, for instance, temperatures are actually going to get colder slightly over time instead of getting warmer. So it'll be important to look at the future climate conditions for Santiago and get an understanding of which passive design strategies are going to be needed in the year 2080 versus what is necessary now.
And again, even though temperature charts give us a very valuable information, the charts that are going to give us the clear picture of how the weather is going to impact our city is the UTCI charts. So as you can see, there's a couple of heat stress moments nowadays in Boston throughout July and June. But by the year 2080, this is going to extend from early June till like mid-September. And the heat stress is going to go from early in the morning till late at night. This is something to take into account, as Heather was saying, because you want to make sure that your building responds to the local climate, not only now, but 100 years from now. And probably you're going to have to account for passive cooling strategies for the year 2080 more than for the year 2020. And finally, we have the windrows. And something that people don't understand is that the way in which you interpret windrows is by looking at the colors over here. So really important, you got to understand your legend. What these colors are telling you are the wind speeds. And what these circles are telling you is the increase in terms of wind speed. So something really important, the longer the arrow doesn't mean that the winds are faster or have higher velocity. So this length, the length of these lines or the length of these polygons represent the predominant winds. So the longer the length, the more predominant from that side the winds are going to be. And the shorter the length, the non-predominant winds are going to come from there. Red colors represent high-speed winds. Light colors are going to represent low-speed winds. But again, this polygon, for example, the one that's pointing straight south, even though it's pretty long, it's not having a lot of red colors, which means that there's some predominant winds coming from the south, but those winds are not going to have a very high speed.
So this is telling us that in Boston, throughout the year, winds predominantly come from the northwest and sometimes from the southwest, although the northwest slightly more. Winds very rarely come from the north, from the northeast, much less time of the year than the other times. The other thing to note is this is an annual windrows, but when you run your script, there will actually be 4 different windroses off to the right that Juan showed before. Now, these break it up by season. So you can see here in Boston that in the winter, there's actually very high wind speeds to the point of the coloring. So there's very high winds coming from the west and the northwest in winter in Boston. Whereas in the summer, the winds have a much lower speed, and they are coming more evenly from the southwest and the northwest. So this might change your design responses. In Boston, if you want to have a comfortable public space, you probably don't want to put your plaza to be very exposed to the western or northwestern winds, because those winds are just going to kind of whip through in winter and create a very uncomfortable area. Whereas, a better location in Boston might be a more protected, south-facing courtyard that allows protection from the northwest wind, allows you to get solar radiation from the sun, and creates a more comfortable zone.
And that south-facing courtyard, for example, is going to receive some of the southern winds, predominant winds that are going to happen during the summer.
If natural ventilation was a consideration for this climate and something you wanted to look into, you would look into the times of the year when natural ventilation is desired, when it's too warm to be considered comfortable, and see where the winds are coming from predominantly during that time, and see whether cross ventilation or stack ventilation might be an option.
Correct. And again, the colors are going to represent your wind speed. The length of the polygon are going to represent the predominancy, so where the winds are coming from.
Okay, and our final chart, and my most favorite chart, is the psychrometric chart. So this can be kind of complicated, but I'm going to break it down and make it very simple for you. The reason we like this chart is because it does aggregate a lot of data together, but it also allows you to really quickly determine which passive strategies will work for your particular climate. So across the bottom, you have air temperature going from -5 all the way up to 115 degrees Fahrenheit. The arches in the graph represent humidity. So starting from the bottom or the outside of it represents 0% humidity all the way to the top of the chart, that's 100% humidity. So the other thing we're looking at here is this graph actually takes every hour of the year in Boston and plots it in terms of temperature and humidity across this chart. So the more hours that fall into a particular block or a particular square, you'll see denoted with the warmer colors. So the reds, the oranges, the yellows have a high number of hours, whereas the dark blues have a low number of hours of the year that fall into that. So very quickly, you'll see that there's an aggregation of hours of the year in Boston that's hovering around the 55-degree temperature range at around 90% humidity. So that tells you that in general, Boston is below the comfort zone. It's a little too chilly to be considered comfortable. Now, the comfort zone is the polygon that's outlined in red right now. That's the ASHRAE-defined comfort zone that goes roughly from 68 degrees to 75 degrees, although that changes depending upon the amount of humidity that's in the air. So you'll see there doesn't seem to be too many hours that fall into the comfort zone right now. And actually on the top left of this graph, the chart will show you the percentage of the year that falls into that polygon. So in Boston, only about 6% of the year is considered comfortable. Otherwise, you need heating or cooling to be comfortable. To the right of this, those are all of the warmer hours, and you'll see there aren't many hours of the year that are warmer than the comfort zone. And so passive cooling strategies, which we'll go through a few of them, might not have as much impact. For instance, evaporative cooling would not be a good strategy for Boston because it's only applicable about 3% of the year, less than that. Another passive cooling strategy would be thermal mass and night ventilation. Although this is slightly more percent of the year, it's still not a very high strategy to pursue in terms of delivering more comfort. Really, because the bulk of the hours in Boston fall to the left of the comfort zone, we need to be looking at passive heating strategies, as we mentioned earlier. So internal heat gains, if we're able to capture those and use those to reheat our building, then we can increase comfort by about 25%. So what internal heat gain means is we're creating a building that is more insulated and airtight and allows us to maintain all of the heat gain that's coming from the people and the equipment that are in the space instead of just losing it to the exterior and having to provide that heat through a mechanical sense. So in this particular climate, insulating your envelope and creating it airtight can have a big impact on the amount of heat that you need to supplement a building with.
And again, what this chart is telling us and is proving our theory that Boston is pretty much a predominantly cold city in which passive heating design strategies are going to have a bigger impact in terms of thermal comfort than passive cooling strategies.
Now, if we were to look at, we don't have this data now, but if we were to look at the 2080 climate file for Boston and the temperatures are rising, you would see that passive cooling strategies start to become a little bit more important and a little bit more valuable. So that might be something that would be considered. Now we're going to talk about design application. So once you've identified which passive strategies work best for your climate and which ones you want to apply to your building, there's a really great resource out there that was created by the Architecture 2030, the people who created the Architecture 2030 Challenge. And it's called the 2030 Palette. So the 2030 Palette aggregates a variety of passive design strategies and information of how to apply those to your design into one place. So they do it at multiple scales. It's at the regional scale, the city and the town scale, the district scale, site scale. But really what we want to look into here, and which will be the most valuable most likely, is at the building scale. if you jump into this scale, there's a variety of passive strategies that you see outlined here that you can kind of jump into further. So if, for instance, you have identified that natural ventilation would be a good strategy for your climate, you can click on cross ventilation or stack ventilation and get a lot more tools and information of how to apply stack ventilation to your project or how to apply cross ventilation to your project and what are the important things to consider. Similarly, if you're interested in using thermal mass or you're interested in looking at more into shading and window to wall ratios. So we highly recommend using this website. I think it'll be really helpful for you as you're trying to figure out how to apply your passive design strategies to your design.
And something that's also extremely useful about this webpage is that it's going to provide you case studies and references of projects that have used this passive strategies in the past successfully. So we highly encourage you to take a look at this webpage. But at the end of the day, you gotta do something with all this data. So you gotta express all that data in your design, and you gotta make sure that all this information, all these charts, all these tools that you've been using to get weather analysis and weather assessment, it's applied to your design. And how do you express that? By either using diagrams that represent your strategies in a graphic way. So these diagrams can be either hand-drawn or it can be computer-generated. And it can be as simple as just expressing a volume or a cube with your design intentions and showing how you're applying those passive design strategies into your building. Or it can be as complex or a little bit more elaborate into applying all the strategies to your entire building. So this, for example, is the sketch of a project that's pursuing net zero here in Washington, D.C., in which we were showcasing all the different passive design and all the sustainable features of the project. And this was really helpful to help understand the client in a very basic language, how the project was getting to net zero and which were the sustainable features of the project. But you can take it a little bit further ahead and like raise the bar slightly and just go into a wall section or into like a detail of your project and show how you're applying strategies like shading, how you're blocking the solar radiation, but at the same time reflecting light into your space and allowing for views to happen through the shading. And even go as deep as generating a detail of the shading device. And as we were saying, it doesn't necessarily need to be hand-drawn. You can do computer-generated graphics, showing your intention and showing your design strategies and how you're applying them into your design. So it can be something as simple as using blocks, using bars, and showing how the sun is affecting your program, showing how you're orienting your outdoor spaces versus your indoor spaces, showing how you're integrating the context based on the analysis you just did. Or it can be something a little bit more elaborate in which you take a 3D section or you take a 3D image of your building and start showcasing how light is entering the space or how wind is affecting your space or how you're applying strategies such as PV panels, natural ventilation, or daylight harvesting.
So on that note, thank you for listening today. If you have any questions, Juan and I are around to assist you through this process. We're not going to be running any of the analysis for you. We're really encouraging you to take a stab at doing that yourself, but we're here to help with interpretation and any questions you may have that arise along the way.
And again, even though this is focused mainly for the Chile competition, it is highly encouraged for all the different design teams throughout Perkins-Eastman to use the script to run this weather analysis, to understand the local weather conditions of each one of their projects as almost as a mandatory basis, to understanding since the early stages of the design process how the weather works, how the sun is impacting my side, how the wind is impacting my side, what are the thermal comfort levels of the different areas I'm working on. And we highly encourage the different design teams to use this script and to use this information and to use these tools we have in-house. As I showed you before, this script is located in a publicly available drive, in the S drive, and everyone have access to it.
Okay, thank you very much.